Good afternoon, everyone. My name is Mansi Tripathi. I am TA for the course Environmental Chemistry. So, this is week 2 of the problem solving session. So, I am here to first of all revise whatever that has been taught in this lecture. After that, we will go through some typical assignment as well as examinations problem that were the part of the syllabus, and I'll help you in solving them. After that, in case of any doubt, you can ask me in between or you can ask me at the end, even from this session or the previous one. So I have shared my screen. So we'll start with some introduction and the other problems. After the session, I will share the video and the PPTs with you. So the week 2, this is a recap of week 2. This week was all about component balance, reaction kinetics, types of reactor, and mass balance. So we will see all these four one by one. So the first thing is, whenever we want to, the first and the most important thing that we will use in whole of this syllabus in whole environmental chemistry is we will solve some certain sets of equation either manually, or we can use MATLAB Excel program, or there will be one software usage also, Visual Mintech, so that we will see in future. So for now, for solving the systems at equilibrium, we will use various concepts. So for solving any system, four types of equations are required depending upon the number of unknowns. If there are one or two unknown, one or two equation is enough. So depending upon the number of unknowns, the type of uh, number of equations will increase. So how these equations come? So either we use mass balance concept or the charge balance concept. So in most of the cases we use mass balance because this charge balance is not relevant in many cases. So that's why mass balance is mostly used. If the number of unknowns are still more than the number of equations of mass balance, we go to equilibrium equations. The fourth concept is component balance. Here in this lecture, most of the time we will focus on component balance. So there are few steps that we need to do to uh, do this component balance analysis. So first of all, we identify the species which are at equilibrium. After that, we will identify the number of components to form all of these species. So the word minimum here is important. So there are various sets of components which will make up this all of the species. So we need to identify those components. Then we have to write the formation equation. Okay, formation equation, in writing this equations, what we use the components that we have selected for writing, for identifying the species. We will prepare W after that, and from this W we will write the equations for component in terms of species. So we will see example also with this. So let's take one example and write. So let us say there is one equation. Sir has taught this example. I am repeating this again. HAC. On equilibrium, it is forming H plus and AC minus. Okay, so we'll solve this in some other panel so that it becomes easier for us. So let us take HAC, which is in equilibrium. It will form H plus AC minus. Okay. So first of all, we need to identify the species. What all species will be there? So one will be HAC, second will be H plus, and third will be AC negative. As sir has explained, this proton we will always take as species, and the most deprotonated form also will be considered as species. Apart from that, any another number that we can take as species. Now we will look into component. Since this thing will also be there along with water dissociation, so this water dissociation also will be considered. H plus OH minus. So one more species is added, which is OH minus. Why H2O is not taken? Because it is constant. So component will be our H plus and AC minus. So now we will write the different formation equation for all the species. HAC, H plus, AC negative, OH negative. For HAC, what will be? H plus AC negative. For H plus, it's H plus. For AC negative, it's AC negative. And for OH will be H2O minus H plus. The next step is the W. In the column, we will write all the species, and in the row, we will write our components. For preparing of HAC, it's 1, 1. For H plus, it's 1 and 0. For AC, it's 0 and 1. And for OH, it's minus 1 and 0. Now we have our recipe. This is the initial thing that we have kept. So for preparing of HAC not, it is 1, 1. Now we will write the equations. For preparation of H plus total, 1 into HAC. Okay. Now this 1 into H plus, AC is 0 and OH is minus 1. Minus 1 into OH negative. And what is the recipe? HAC not. Similarly, we can write for AC negative. HAC plus AC negative is equal to HAC not. Okay. So if we want to count the number of unknowns, so how many number of unknowns are there? You can see this thing we have added, so that's why this is known. All other things are unknown. So means number of species is equal to number of unknowns. Number of species is equal to number of unknowns. Okay. So how many unknowns we have? 4. But how many equations we have from component balance? It's 1 and 2. How we will get the other 2 equations? We can get them from equilibrium. So Ka, dissociation constant, will be so. Hi. So I was just explaining how are we writing all these equations, the steps that we are following to write the species and components so that we can write the formation equations. So I was just explaining that by using the example of HAC. Sir has already taught this thing, so I was just in re-encapsulating whatever he has taught. So for you, I will revise it for once. So as I was saying that HAC means acetic acid can be dissociated into H plus and AC negative. Similarly, the water molecule can also be dissociated in H plus and OH minus. From here we can get all those species. So species are our HAC, H plus, AC and OH negative. So what is component? Component is the minimum number of building blocks that can be used to make up all the species. So the component that we usually choose is H plus and the most deprotonated form, AC negative. From here we wrote the formation equation. These are the different species. So how we are getting these species? By writing the number of components. Like for HAC it will be H plus plus AC negative. H plus, obviously just one H plus is required. AC, we have similar component as species, so it can be written for OH is H2O minus H plus. From here, we prepared the table. So table column, we will write all the species that we want, and in the row, we will write the component. And we will just assign the numbers 1, 2 or 3 depending upon how much component is required to make up a particular species. This is the recipe. From here we can write just the equations. And we also came to identify that the number of species is equal to number of unknown. Here we can see number of species is 1, 2, 3, 4. But from the component balance we were able to get only 2 equations. So how we will get the other equations? That we can get from equilibrium equations. So equilibrium Ka, if we look at the equation, it will be acetate H plus divided by HAC. So this is our one equation, equation number 3. And the fourth equation will be water dissociation constant. So Kw is equal to H plus OH minus. So this is our fourth equation. So by using these 4 equations, 1, 2, 3, 4, and there are 4 unknowns and 4 equations. So this problem can be easily solved. So moving towards the concept. So I was telling for writing what all the things we need to do for writing the component balance. First step 1 is identification of the species. Second step is identify minimum number of component to form all the species. Third is to write the formation equations that we have done. Fourth step is the preparation of table. And the fifth step is write equation for component in terms of species. Okay, here this minimum is important because we need to identify only means the minimum components that can help to form all the species. We cannot just write everything. We need to identify the minimum sets of equations. The next concept was reaction kinetics. So what is reaction kinetics? It is the characteristics of the reaction and it defines that how fast the reaction is going. So what was equilibrium? Equilibrium used to say that how far the reaction is going, how far. But kinetics is how fast. So this is what defines kinetics. After that, we also learned about the rate of reactions. So one was overall rate of reaction and the second was volumetric rate of reaction. So we mostly use volumetric rate of reaction because it gives correct representation. We also learned about sequential reaction. So what is sequential reaction? Reactions which are happening either parallelly or in series. Like from A, if we are getting two compounds, B and C. So this is called sequential reaction which is happening parallelly. So we also understood that if there are two rate constant K1 and K2, and if K1 is very fast than K2, means formation of B is very fast as compared to formation of C, then if we look at the reaction, we will see it can be stated, if we look into the time of reaction, we can say that this reaction will almost, the time of reaction, the rate of reaction will almost be equal to just the formation of C, because this B is very fast. So that's why this parallel reaction can be approximated to reaction directly going to C. Similar things can happen to this series reaction. A is forming to B and B is forming C. So here same thing can happen if the rate of reaction is K1 and here it's K2. Then if K1 is many times faster than K2, we can say the reaction, this A is directly being converted to C. Okay, because there will be A will be coming down. So there was the graph that explained this thing. So if this is A is coming down, C is forming. Okay, so this is C, this is A. But if K1 is many times greater than K2, what will happen? There will be accumulation of B. So how this thing will look like? That instead of, oh, okay, instead of A going to B and B going to C, because A is converting to B at a very fast speed, it will look like that only B and C are there. So if at a point of time you will see that only B and C are visible. K is less, A is less. So if K1 is very fast than K2, then it will look like that only B is being converted to C. There is no concept of A. If the reaction between A to B is very fast, it will look like this. Okay. So this is how this rate constant and concept of parallel and sequential and series reaction are used. We understood rate constant also. And what is the rate limiting step? Rate limiting step is the slowest step. So here, if in this reaction we see K1 is very fast than K2, so what is the rate limiting step? K2. K2 part. So B to C is the rate limiting step. Other thing that we understood was the reaction kinetics. So what is reaction kinetics? So first we understood about the reversible and irreversible reaction. So what kind of reactions are they? So in most of the cases, like A is being converted to B and B is being converted to A. So this is forward reaction. So this is rate of forward reaction and this is rate of backward reaction. What is what are reversible reaction? Reversible reaction are those reaction in which rate of forward reaction and rate of backward reaction are kind of in the same order, not similar. If they are similar, that this thing will be considered in equilibrium, but they are of the same order. Okay, there is not big difference between the two. But what is irreversible reaction? Irreversible reaction are those reaction in which rate of forward reaction is many times higher than rate of backward reaction. So we say that the reaction is only going in one direction. It is not coming back. So that is why it is called irreversible reaction. So as we see that it depends upon the rate. So that's why it is kinetically controlled. Okay, it is controlled by kinetics. If the rate of forward reaction is many times higher than the backward, it is called irreversible. So that is why it is kinetically controlled. And after that, the equilibrium constant is higher for the irreversible reaction. So how this is happening? Let's say A plus B is there. It is being converted to C plus D. Okay. So because rate of forward reaction is very high, almost all of the A plus B, all of the reactant will be converted to product. So what is equilibrium constant? Is product of product divided by product of reactant concentration. Since all of the reactant is converted to product, there will be very less of product and high of very less of reactant and quantity of product will be very high. So overall what will happen? This K will be very high. Okay. So for equilibrium constant is higher for irreversible reactions. Now we will learn what are the concepts on which rate of reaction depends. So it depends upon the concentration of reactant. Okay. Rate only depends upon the concentration of reactant, not of product. So in case of, like, if we assume this reaction or this reaction, rate will be equal to some rate constant and the concentration of reactant. Okay. Or if we look into this case, so R is equal to K of A. Secondly, it depends upon the temperature. So for solving the rate constant for different temperature, like for example, if we know temperature at 20 degrees Celsius, we want to know at 30 degrees Celsius, so Arrhenius equation can be used. So sir has taught Arrhenius equation, you all have seen, but simply it can be approximated for, actually it is different for different scenarios. So there is one such scenario, one such empirical equation. It looks something like this. K at certain temperature is equal to K at, let's say, 20 degrees Celsius, theta, this is Arrhenius constant, T raised to power T minus 20. Okay, this is one such equation. You can, instead of 20, you can use not or any other value for which K is given. Theta can be varying 1.305, 1.7, anything. It will be given. It depends upon the activation energy. Okay. The other thing is stoichiometry. So stoichiometry helps us to define or find the relationship between the rate of different compounds with the rate of reaction, rate of formation of different compounds, rate of formation of different compounds with the rate of reaction. So here stoichiometry is used. Now the final concept that we understood in this week is the concept of reactor. So what is reactor? Reactor is basically the volume where an experiment or any activity or any treatment, these things are performed. Excuse me. Okay. So reactor can be of various types. The most common reactor is batch reactor. Other thing is completely stirred tank reactor. And the next is plug flow reactor. What is batch reactor? Batch reactor is kind of reactor which is completely mixed. So this is the sign of mixing. Wherever this sign comes in anything, that system is assumed completely mixed. And it is closed reactor. What is closed reactor? Closed reactor means there is no incoming, no outgoing. If in any reactor, like for example, if we are taking this water bottle, it is a batch reactor. I am mixing it, it is batch reactor. But if I am removing some water or drinking some water out of this, it will no more a batch reactor. Okay, it is a batch reactor until the time there is no incoming or outgoing. Just as soon as there is any incoming or outgoing, it is no more a batch reactor. It will convert to completely stirred tank reactor. Okay, so that thing is very important. One reactor can be converted from one form to another just by changing the flow and by changing the condition. So okay, so we cannot always say a bottle is a batch reactor, but it is a batch reactor unless there is no incoming or outgoing. I am not filling water, I am not taking out water. Then only it is a batch reactor. Okay, of a fixed volume. Volume is fixed. However, volume can also be fixed in the completely stirred tank reactor. How? If the rate of incoming is equal to rate of outgoing, the volume will be constant. Okay. So this is batch reactor is closed reactor. The examples can be beaker, okay, or glass or anything you can think of. So this is the equation of the batch reactor, that rate of change of concentration with time is equal to rate of formation minus rate of loss. The next reactor is completely stirred tank reactor. So it is similar to batch reactor, completely mixed, but there is always some incoming and outgoing flow. So this is completely stirred tank reactor. Here what happens? The volume which is inside the reactor can be controlled by varying the flow. If the incoming and outgoing flow are same, volume will be constant. If incoming flow is more than outgoing, then there will be overflow, right? Volume will increase. If incoming is lesser than outgoing, volume will decrease. So for this, we have this equation. We know how to solve all these equations, or how to derive all this equation. If you want, we will revise that also. So other thing is plug flow reactor. So here the concentration changes with distance. So this is the formula for the same, dc by d theta. Here theta is HRT, hydraulic retention time. It depends upon rate of formation minus rate of loss. So for the sake of revision, we will derive for one or two reactors. let's say batch reactor. So from the basic equation, so what was the basic equation? This was the basic equation. So I will use some other color pen. So VC by dt is equal to Q in C in minus Q out C out plus V RF minus RL. Okay, so this was the basic equation. So I will write it, then it will become easier for you to understand. dC by dt is equal to Q in C in minus Q out C out plus RF minus RL. Okay, then we know that there is no incoming and outgoing, so this part will become 0. So what we will get? We will get this V dC by dt is equal to RF minus RL. Yes, here volume term will also be there. Sorry for the mistake. Volume will be cancelled by volume. So finally dC by dt is equal to RF minus RL. Now let's take a equation. Okay, like let's say A is being converted, or let's say equation A plus B is converted to C plus D. Okay, let's say that the concentration of B or the volume of B is many times higher than A. Okay, so let's say B is constant, or let's take a simple case. Let's forget about this. Let's take a simple case. A is being converted to B plus C. Okay, so what is rate of formation of A? A is not forming, so rate of formation of A is 0. What is rate of loss of A? It will be constant, rate constant, and it will depend upon the concentration of A. Okay, let's put this in the equation. So dC by dt is equal to minus K A. Now this concentration, it was generic form na, now we will write it as A because we are solving for A. So what will happen? It can be solved by integration 1 by concentration A dA is equal to minus K dt. When we will integrate it, integrating and putting constant everything, so constant, putting the condition at t is equal to 0, A is equal to A naught. Okay, this will be the condition for constant solving. Then what we will get? A is equal to A naught e raised to power minus kt. So this is our equation if we consider the rate of reaction as first order. So this thing will change if we consider rate of reaction as second order. What will happen? This is our basic equation, right? If we consider rate of reaction as second order, then what will happen? Rate of loss is equal to K if it is considered second order, right? This is second order reaction. Then dA by dt is equal to minus K A square. Now for integration, A square dA minus K dt, then we can solve this equation, okay, by integration, all these things. So similarly, so I'm not writing the answer, I need to calculate it, it will be time taking. So similarly, we can write for first order, second order, zeroth order, third order, any order of reaction by using this thing. So so this was for batch reactor. So similarly, we obtained for plug flow reactor and for completely stirred tank reactor. Okay, similar expressions can be obtained, and it is not only applicable for the first order, zero order, all the equations are applicable for other orders. So I have written for other orders, so I have written for other reactors, so we will see them. So for plug flow reactor, V dC by dt, Q in, C in minus Q out, C out plus V, Vf minus RL, RF minus RL. Similar. So here the best concept is to take a strip in which the reaction is completely mixed. So we have taken a small strip, that is dz. So the concentration to the left of dz is Cz and concentration to the right is Cz plus dz. Volume is A dz. So we will substitute this volume in the first equation. We got A dz dc by dt is equal to QC, because Q is same flow is going in and same flow is going out. So Q can be taken as common, and in the bracket Cz minus Cz plus delta Z. For this volume also A dz Rf minus RL. Dividing this whole equation by A dz, we will get dc by dt is equal to Q by A dz, Cz minus Cz plus delta Z plus Rf minus RL. Now we can write Q. Q is nothing but area into velocity, right? So this is what we have written in the differential form. Q is equal to A into du. U is velocity here. Vu is velocity here. Velocity. So du by dz is what? 1 by d theta. Theta is what? Hydraulic retention time, HRT. So dc by dt is equal to 1 by d theta, Cz minus Cz plus delta Z plus rate of formation and rate of loss. So dc by dt is equal to dc by d theta. How this dc came? The change in concentration in the differential unit can be written as dc. Okay, this form is called differential form. And this form is called discretized form. Okay, this is differential form. So thus this discretized form is written in terms of differential form. So this is the equation that we got. Now if this system is in steady state, what will happen? dc by dt is equal to 0. There is no change with respect to time. So that is how we got dc by d theta is equal to Rf minus RL. So similarly, if the reaction is first order reaction, rate of formation minus rate of loss is equal to minus Kc. So this thing can be written. Coming to other form is CSTR. CSTR is kind of batch reactor where which is not a closed system. It means there is some incoming flow and there is some outgoing flow. So similar equation can be written. This is the basic equation. Similar equation can be written. Here we will divide the whole equation by V. If we are dividing by V, we won't get this. So dC by dt is equal to Q by V, C in minus C plus Rf minus RL. Here Q by V can be written as theta, right? Now at steady state, dC by dt is equal to 0. Just putting this as 0, we will get this equation. Similarly, if we write the equation for first order reaction, we will write minus Kc, and this when solving, we will get this. So this is our basic equation. Okay, so these were our equations. Just in place of Rf minus RL, we can put any order, 0 order, first order, second order, third order. You all can uh, try writing equation in different orders, and we can discuss them in the next week. Now coming to questions. So coming to the first question, consider the dissolution of sodium bicarbonate in water. Species at equilibrium for the above dissolution are, we have species, we have all the species. Which of the following groups can be chosen as component? Okay, there can be many groups of component, right? What is component? The minimum number the minimum number of building blocks that can be used to form all the species. Okay, that is called component. So please try to find the answer for this question. Okay, please write the species. Species are there. Please write the components part. That is the step 2 of the component balance. So please try to find out the answer. You can write in the chat box. I'll give you a minute to do this. Okay, we'll see the answer now. So answer is B and D. Okay, so okay, your answer was A and D. See, A cannot be the one because we know what is sodium carbonate. Sodium bicarbonate is NaHCO3. So for forming sodium carbonate itself, we need carbonate also, right? So that's why A is not the answer. Okay. For writing that, we need sodium carbonate as well, no? So that is why answer is B and D. You have written D part, no? Yeah, D part was correct. A cannot be the answer because we need this carbonate entity also. Okay, which is not there in A. A has everything but carbonate entity. So that's why this thing is deleted. Apart from that, for making OH, we can easily make OH by H2O minus plus H plus. No. So that is why OH need not to be written separately. Okay. The important point while writing species is it should contain all the components, minimum components. Apart from that, there should not be relation between the two. Okay, for OH and H plus, there is this relation now. That's why it cannot be considered as the group of component. Moving towards next question. Moving towards next question. Sodium acetate is dissolved in water to undergo the following reaction. We can see this reaction. Okay, we can see this reaction, right? NaC is converted to Ac plus Na and the H2O reaction. So following details were obtained after the analysis. We know species and we know the component as well. Please choose the correct option for the concentration of components. Okay, you can write the answer for this question, then we will see the solution for this one. We need to write the step 4. So we have done the step 1 species, step 2 component, step 3 we can write the formation equation, step 4 is the W and step 5 is these equations. So please follow all the steps and write the equation for the same. You can write the answer in the chat box. I'll give you 2 minutes. Then we can see the solution for the same. Okay, we'll see the solution now. This option B, C, and D. So how do we got these options? We have species and components, right? So for writing all the, let's go to step number 3, that is writing the formation equation. So what all the species are there? Na plus, Ac minus, H plus, OH minus, and HAC. What are the components that we will use? Na plus, here Ac minus. For H plus, only H plus is required. For OH, it will be H2O minus H plus. For HAC, H plus plus AC negative. Okay. Now coming to table U. Na plus, AC minus, H plus, OH minus, HAC negative, Na plus, H plus, AC minus. For Na plus, it's 1, 0, 0. For AC, 0, 0, 1. For H plus, 0, 1, 0. For OH, 0, minus 1, 0. For HAC, 0. Um, for HAC, 1 and 1. Okay. Now when we will write the for Na plus, we have just this one. So Na plus total. For AC total we have 2. So what are these two? One is this and other is this. So AC negative plus HAC. So option number C is also correct. For writing for H total, we have 3. This and this. We have 3. So what are all these 3? H plus minus OH plus HAC. So that's how B, C, D, 3 options are correct. Why the first option is wrong? First option is wrong because what we will do with this part? This part is not required. Okay, it does not H total does not matlab AC does not contribute anything in H total. Similarly, sodium also does not contribute anything to H total. That's why. Okay, now you understood. You have not given option C as the solution, but look at the option C. When we do for AC, two things are only needed, AC and HAC. That's why option 3 is also correct. Okay, let's move towards next question. Question number 3 is a memory based question or just question of understanding. There is no numerical. A sequential reaction occurs in the following 3 processes. This we have discussed, right? A is converting to B, B to C and C to D. These are the rate constant K1, K2 and K3. So which step is the rate determining step? Rate determining step is what? The slowest step. So which one is the slowest step? Please let me know. Then we can see the solution for this question in a couple of minutes. Please take your time and write the answer for the same. Think again. Your answer is wrong. Please think again. We are talking about the slowest step. Okay. So which among this is slowest? From this equation we can see K1 is equal to 100 times of K2, which is 100 times of K3. K1 and K3 are equal. So if K1 is correct, K3 will also be correct. Okay, K1 and K3 are equal, and these are many times faster than uh, K2. No, I'm saying if K1 is correct, then only K3 is correct. I didn't say K1 is correct. If it is correct. Okay. Fastest, we are talking about the slowest steps. So if we look at this, K1 is equal to 100, K2 is equal to K3. So what I mean to say is, if for doing something, we are rate constant is K2. Okay. So for doing the similar thing, K1 is 100 times faster. Okay. If K1 has to take one step, if there is something called K1, if it has to take one step, then for the similar distance, K2 has to take 100 steps. Okay. For example, if something wants to go from this to this, from point A to point B, right? If K1 wants to go, huh? One step will be enough. One step. But if the same thing K2 wants to go, it has to take 100 steps. K2, 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 100 steps. So which one is slow? K2 is slow. Okay? Because K1 can go in one step, but K2 has to take 100 steps. So which one is slow? K2 is slow. That's why the correct answer is B. Second step is the slowest. Yes, very good. Okay. So these things should be understood like this. You can draw all these things and try to understand the question. That for similar distance, K1 just one step, and for K2 it should take 100 steps. So it's like K1 is father and K2 is very small baby. For similar distance, it should take number of more steps. So that is the rate limiting step, right? When a father and the baby wants to go for shopping or anything, baby is the one which will take time, right? Father can just go, but baby, because of small steps, because of many other resistance, baby will take time. So what is the, but they want to reach the shop at the same time. So which one is the, which fact is there which is delaying this process? Baby. So baby is the slowest step. Okay, that is rate determining step. Coming to question number 4, which of the following statement is are correct? Means more than one statement can be correct. Okay, consider giving reaction below. So this is our reaction. We need to find out the reversible and irreversible reaction. So please try to answer this question. I have given the answer for this question in the text in the introduction part itself. So write the answer for this question. We will see the solution in a while. Okay. Okay, we'll see the solution now. So the option A and C are correct. So you're right by this. So irreversible reaction in which things are going only in the forward direction. So rate of forward reaction. Just a second. Just a second. Yeah. Here, these are A to B is considered irreversible when the rate of formation of B, okay, RB is rate of formation of B. RB is forming at much faster rate than RA, means rate of forward reaction is many times greater than rate of backward reaction. So here B is backward, okay, don't get confused. And here B is rate of formation of B. I should have written it like this, capital B, for easy understanding. Okay. So rate of formation of B is much higher than the rate of formation of A. So that is why it is a irreversible reaction. Okay. And for irreversible reaction and for rate determining step is the slowest step that we have discussed earlier as well. So option A and C are correct. Moving to question number 5. 1 gram of solid calcium sulfate is added to 1 liter of pure water. Okay, 1 gram of solid calcium sulfate is added to 1 liter of pure water. Some of the solids then dissolve according to the following reaction which have equilibrium constant of 10 raised to power minus 4.85. The concentration of Ca2 plus at equilibrium is 10 raised to power minus x moles per liter. Find the value of x. The concentration of SO4 or sulfate at equilibrium is 10 raised to power minus 1.87 moles per liter. Please solve this question. We will see the solution in the while. We need to find the value of x. It's very simple question. Just you need to use the equilibrium. So I will write also K is equal to Ca2 plus SO4 2 negative divided by CaSO4. And this is solid. Okay. So one hint, when in a reaction things are involved in solid form, the concentration is considered as 1. Also it is written if 1 gram of solid calcium is dissolved to 1 liter of pure water. Okay, the equilibrium is concentration is considered as 1 for any pure liquid like H2O or if things are there in solid form. So K is equal to Ca2 plus and SO4 2 negative. Please try to solve this question. We'll see the solution now. So, what is K? Okay, we'll see it. So, what is K? 10 raised to power minus 4.85 is equal to calcium 10 raised to power minus x multiplied by 10 raised to power minus 1.87. So, by solving, we will get minus 4.85 is equal to minus x plus 1.87. So 4.85 minus 1.87 is equal to x. This is the power rule. That's why this subtraction will work. So I have the solution. So this is the solution. 2.98. So when we will subtract these values, okay. So x value is 2.98. So 10 raised to power minus x value is 2.98. Okay, this is our solution. So moving towards next question. A study that investigated the reaction of bisphenol A with hypochlorous acid revealed that even if all the PPA reacted, hypochlorous acid will decline very less and could therefore be treated as approximately constant under the experimental condition. The rate expression can be described as, so this is our rate expression. The initial concentration of 0.3 micromole per liter total BPA and 18 micromole per liter total OCl at pH 8 and the KF is rate of formation is 150 liter per mole per second at this pH. How much time would be required to destroy 75% of BPA in the solution? So this is a reactor 1 question. We have the total BPA, we have total OCl value, we have the KF value. We need to know how much time would be required to destroy 75% of BPA. Okay, please try to solve this question. We will see the solution in a while. We have KF, okay, we have everything. We have KF, we have BPA, we have HOCl, and we need to find first of all RBPA, rate of formation of BPA, okay. So RBPA is equal to KF is 150 liter per mole per second, BPA is 0.3 and HOCl. So it is saying that HOCl will decline very less. So we have OCl, but here HOCl is given. So how we will write this? This answer for this question is hidden here. Hypochlorous acid would decline very less and could be therefore treated as approximately constant. How? HOCl by this reaction H plus OCl negative. By using this reaction we can write for HOCl. So please take a pause, try to solve this question. We will see the solution in the while. I have given this many hints. We will see the solution now. So R is equal to minus K BPA plus HOCl. Since because the concentration of HOCl is constant, so that is why, because in that reaction, in this reaction, I gave you the reaction, right? Sorry. This reaction, HOCl dissociated to H plus OCl negative. Because HOCl is consumed very less, so the amount of HOCl can be approximated to OCl. Okay, so that is why we will use 18 only. So 150. Okay, we need to find out BPA percentage, right? So BPA into this HOCl. It is 18 into 10 raised to power minus 6. So R is equal to rate of formation is 0.0027 into BPA. Now remember the equation for batch reactor, because why this thing, all these things are happening in batch reactor, right? So what was the equation? dC by dt is equal to rate of formation minus rate of loss. Okay, so this rate is given as R is equal to minus K BPA HOCl. This rate is only given, right? So this is a similar thing. We have written this equation. When we will solve this equation, we will come to this equation. Remember, I told you equation like C is equal to C naught e raised to power minus KT. So this is the same equation. For destruction of 75% BPA, if 75% BPA is gone, how much is left? 25%. So that is why here we have 25% of BPA. So T we got as 8.56 minutes. So this is our answer. I will share this PPT with you so that you can revisit it again and again, and in case of any doubt you can ask me as well. The next question is, which of the following class of reactor can be used to model calculation of 5-day BOD of wastewater in a beaker? Please try to solve this question. BOD means biological oxygen demand. Such kind of experiments are done in beaker. So what kind of reactor can a beaker be considered? Plug flow, batch, or completely mixed? Okay, you are saying completely mixed. So tell me, in a beaker, is any incoming and outgoing during the BOD experiment? See how this BOD experiment is done. I will tell you. When we take a beaker, na, for BOD experiment, we seal it properly for 5 days. It is completely sealed. Even air is not allowed to go in or come out. Okay. So what kind of reactor is this, which is completely sealed? A, B, or C? Plug flow, batch, or yes, correct. So it is batch reactor. Very correct. BOD experiment is done in very sealed environment. The next question is, consider the following reactions occurring in the reactor. Rate of reaction for the first reaction is R1 and this for the second is R2. What is the rate of formation of C? We need to find out the rate of formation of C. Please try to write the rate of formation of C for this thing. Then we'll see the answer in a while. Okay, so how to write this thing? So we will look only for C. In the first reaction, C is forming, right? So what is rate of formation minus rate of loss? Okay. In the first reaction, C is forming. So what is the stoichiometry? It's 2. So 2 forming R1, and in the second reaction we are losing C. What is the stoichiometry? 3. So 3 R2. This is the correct answer. 2 R1 minus 3 R2, that is option D. Okay, 2 R1 minus 3 R2, option D. So this is our correct answer. Just we have to look at the equations and write what uh, what is the rate of reaction and how it is forming and how it is being consumed. Formation and consumption. Simply for consumption there will be minus sign, for formation there will be plus sign, just multiplied by the stoichiometry. So that is how this thing is done. Coming to the second last question. A batch reactor is operating to treat a toxic chemical X present in water. The initial concentration of X was 500 milligrams per liter. So X naught is 500 milligrams per liter. The concentration of X shall be removed to a desirable limit of 10 milligram per liter. What is the target X? 10 milligrams per liter. Calculate the rate constant if the desirable limit is achieved in 10 days. So our time is 10 days. We need to find out the rate constant. Please try to solve this question. It's very simple. We will see the solution in a while. Okay, we'll see the solution. For a batch reactor, C is equal to C naught e raised to power minus kT. That has been explained earlier. Our target is 10, initial is 500. We need to find the K. So, by solving all these things, we will get K as 0.391. The way that you have solved is when there is linear change. Okay, here the way you have solved is like concentration is changing linearly with time. But that is not the case in batch reactor. In batch reactor, constant changes exponentially. Okay, so that is why we will use this equation. Okay, so there is no linear variation, there is exponential variation in batch reactor. So we need to learn this equation for the batch reactor, and this is only applicable for the first order reactions. Okay, if the reaction is second order, this equation will definitely change in a way that we have seen in the introduction part. So coming to the last question. Select the correct statements. One or more options may be correct. So answer is already given, but I want you to understand these things properly. So diffusion phenomena occurs due to concentration gradient. Advection phenomena occurs due to net motion of fluid, or only longitudinal mixing is considered in advection or the lateral mixing. So this answer is already given here. So I'll explain what is advection, what is diffusion. So if we consider a river, an object is kept here, and this is the velocity, this is the direction of flow of river. And if this object moves with the velocity, with the flow of river, it is called advection. Okay. And what is diffusion? If a body is there, sir has given example of perfume, right? There is fan is off, AC is off, no wind flow, everything is there. But if I am opening a bottle of perfume at one location, the person sitting at the next location, at the very far location, will get some smell. So this is because of diffusion. In diffusion, what happens? There is something, some bad smell, good smell, any kind of smell. This smell will start spreading due to concentration gradient. So this phenomena is called diffusion. Okay. So option A is correct. Diffusion is occurs due to concentration gradient. Option B is also correct. Advection occurs due to net motion of the carrying fluid. And option C and D, let's think about those. In longitudinal mixing is considered in advection. Longitudinal mixing is what? Longitudinal mixing is mixing in this direction. And what is lateral mixing? Lateral mixing is mixing in this direction. So in advection, only lateral mixing is considered. Mixing in up and down direction. Okay. Not in the direction of flow. So that's why option D is correct. So that's all for today. Okay. So I'll see you in the next class. In case of any doubt, yeah, okay. I think I have sent it earlier. You can give me your email. Have you given your email? You can give me your email. I will send this to you. Apart from that, in case of any doubt in between the sessions, you can always write them to me, or you can reply to my email that I will send you. Okay, you can give me your email. You can write your email in the chat box. Okay, okay, I will check. You want book for chemical kinetics. Okay, okay. So I'll see you in the next class. Bye bye.